All right, you guys have your reference sheet?
Of course.
All right.
Yes.
So the first thing to review is kinematics, which is the description of motion. Okay? And so the first couple of equations on there tell you about that. So the distance an object travels is equal to its initial velocity times the time, plus 1/2 the acceleration times the time squared, right? That looks familiar?
Of course.
And with it goes that the final velocity equals the initial velocity plus the acceleration times the time, and the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the distance you go. So some combination of that. There's 6 variables, right? There's the distance you go, final initial position. So there's 2 variables there, right? X final,
Yeah.
X initial. There's initial velocity, final velocity, time, and acceleration. And probably the most important thing there to remember is that if there's no initial velocity, the distance an object travels is proportional to the time squared. So if something accelerates twice as long, it goes 4 times as far. Okay? If you, yeah, so if the acceleration is unknown, it has to be constant. But the special case that we study most often is when the acceleration is due to gravity. So in that case, the acceleration equals negative g, right? So g is the 9.81 and it's downwards, so it's negative g. So you're going to get a problem where they say a stone is dropped from a height of 3.5 meters. How long does it take to hit the ground? Right? So if the initial velocity is 0, solving that problem for the time is fairly straightforward. So those are pretty common problems. The thing to remember about kinematics is the graphs.
Yes.
So remember that the most important one is the velocity versus time graph. So in this case, the velocity versus time graph, the slope tells you the acceleration, and the area tells you the displacement. And just be careful. If the displacement is 10 meters, it means you've moved 10 meters from wherever you started. So if an object starts at 7 meters, and then this describes its motion, and the area is 10, what's the final position? It's 17, right? So just make sure you know whether you know about the displacement, which is how far you've moved, or your position, okay, where you are located. The other 2, and so that's the most important one because we get 2 things out of it, right? The acceleration is the slope. The other one is if you graph the position versus time, the slope. So if this one's position versus time, it goes like this. In this case, the slope equals the velocity, right? And if you graph acceleration versus time, then its slope is the jerk. Which we don't care about, we won't use in this course, but more importantly, the area under the graph is the change in velocity. It's how much the velocity changes, okay? So this is, the area is the change in velocity, okay? And the slope is meaningless. So those are that's, the 3 important graphs to know, okay? So that was kinematics. A lab question that comes with that would probably be something like, a student drops a ball from several different heights and records the time it takes to fall and various differences. What would you plot to find the acceleration? So if a ball is falling, right, from rest, what would you plot? So the slope tells you the acceleration. You probably plot the distance it falls on one axis and the time squared on the other. And then the slope would be 1/2 the acceleration, right? So that's kind of the lab questions that go with kinematics. So, I think that's pretty straightforward. They'll ask you some questions with graphs and stuff. The second big idea is dynamics. And so dynamics is what causes motion. And the short answer is forces. Forces cause motions, right? So Newton's 3 laws, F equals ma, is Newton's law the second law, the way we have it. Newton's first law basically says that if there's no external force, if the net force equals 0, the acceleration equals 0. That's what Newton's first law says. Objects in motion stay in motion. Objects at rest stay at rest unless acted on by an outside force, the law of inertia. So basically saying that without a force, an external force, objects don't accelerate. If they're moving, they keep moving. If they're stopped, they stay stopped. If they're moving, they don't spontaneously change directions. Okay? So Newton's second law is more broadly written in terms of the acceleration. It is equal to the net force divided by the mass. So that's more cause and effect. A net force causes an object to accelerate. Even though we write F equals ma to avoid the denominator, that's more cause and effect there, right? Net forces, of course, are the unbalanced component of the forces. So just remember that if an object has, a force going this way of 10 newtons and a force going this way of 6 newtons, the net force is 4 newtons, right? It's the unbalanced part. And you need an unbalanced force to cause an acceleration. If the unbalanced force is to the left, the acceleration is negative. That doesn't mean it's going to move to the left. It might be moving to the right and slowing down. But it's the unbalanced force tells you the direction of the acceleration, the change in velocity, not the direction of the motion necessarily. Okay? A couple of forces you have to know. You have to know that the force of gravity on the surface of the Earth is given by m times g. If you're not on the surface of the Earth, you got to use Newton's law of gravity, which we'll get to in a little bit. You have to know that the force due to friction is always less than, well, it depends. Let me write it twice. The force due to friction on a moving object is equal to mu times the normal force. If it's moving, so I'm going to put K for kinetic. And the force of friction on a static object is always less than or equal to mu sub s times the normal force. Okay? Does that make sense? You know why it's less than or equal to?
It's not moving, so you don't have to find it.
Yeah, so if I push on a block with 10 newtons, it doesn't push back with 30.
Yeah.
It opposes motion up to this point.
Yeah.
And they will ask a question where, a block has a mass of 50 newtons and the coefficient of friction is 0.25 and a person applies a force of 20 newtons, what's the acceleration? You gotta make sure it's enough force to make it move first. Because if it takes 25 newtons to make it move and they apply with 20 newtons, the acceleration's 0. Right?
Yeah.
So just make sure you check that condition if it's sitting still, it's static friction. It is also true that the coefficient of static friction is always greater than the coefficient of kinetic friction. That'll be a multiple choice question. Does that work? Okay? Static friction is always greater. And that's because friction arises because of these imperfections in the surface. And when you're stopped, you kind of settle in deeper than when you're bumping along.
Yeah.
So once you get moving, the oppositional force isn't quite as large. So that you got to know this force, you got to know friction force. Other forces you have to know, those are the two main ones, I think. Yeah, so that was the study of dynamics. An application we did of this, the most important application is the inclined plane. So if you think about an object that's on an inclined plane, you can think about the forces that are acting on it. Gravity pulls downwards. The normal force acts perpendicular to the plane, and if there's any friction, it acts in that direction. Right? And so from that, we derive the fact that the acceleration, if there's no friction, is just the component of gravity going down the track, right? So it equals g sine theta. And if you're confused, think about 0. If the angle was 0, the acceleration would be 0. Here, if the angle is 90, the sine of 90 is 1. The acceleration is straight down, right?
Yeah.
And then also the other thing here to remember is that the normal force on the inclined plane isn't mg. It's mg cosine theta. There's a component to the normal force that is not opposite of gravity. So just be careful there. Okay. Yeah, so that'll move down the plane. And they'll almost always give you 30 degrees. And that's nice because the sine of 30 degrees is a half.
Yeah.
Right? So the acceleration down a plane will be half of g. 30 degrees. If it's less than 30 degrees, it'll be less than half a G. When it's more than 30 degrees, it'll be more than half a G. Give your calculators the whole exam, so you can always work it out.
Really?
Yeah.
How is that?
Yeah, give your calculator the whole exam. Okay. So that was dynamics, and that was kind of all the important things. The next big idea was energy. I'll go with energy. So energy is sort of the accounting system of the universe. It's how we think about what things are worth to us, right? So energy comes in two forms. It's kind of active energy or kinetic energy. So the kinetic energy is something that's actually in motion, and that's 1/2 mv squared. And then there's potential energy, and that potential energy is stored energy, and we have energy that can be stored in a gravitational field. So if you're on the surface of the Earth, that's mg times however high you are from a reference point, right? If you're below the reference point, your potential energy is negative, you're trapped, you're stuck in the hole, right? The big idea is that for an isolated system, the energy is conserved. So if a marble rolls down a track and doesn't lose energy to friction, which is heat, then the energy will be conserved. The big idea was that the mechanical energy at the end of a problem is equal to the mechanical energy at the beginning of a problem plus any work done. And work was defined as the transfer of energy into or out of a system. So you can solve problems, for example, the kinds of problems you end up solving with this is the car rolling along, going up a hill, right? Remember this problem? And you can say, how high is the hill if the velocity here is 20 meters per second, on the top of the hill it's 14 meters per second, right? You can say the kinetic energy it has at the bottom must equal the kinetic energy it has at the top plus the potential, right? So those are the kinds of problems we solve. Or the pole vaulter, same thing, right? Those kinds of problems. You'll most commonly see this probably in some kind of problem that involves a ball rolling down a ramp, and you want to know what is the velocity when it leaves the ramp. Okay? Energy we use to solve problems that involve one object, generally. So if a ball is rolling down a ramp, if a car is zooming down a track or doing something, one object. If there's two objects interacting, we almost always use momentum. Okay? Unless it tells you explicitly the total energy was conserved. But that almost never happens. Okay? So other things, I'm not quite sure where to throw them in. But other things that fall under energy, if something is rotating, it also has energy. And so its kinetic energy due to rotation is 1/2 I omega squared. So it's like kinetic energy, but it's the moment of inertia, the rotational inertia times the angular velocity squared. I'll talk about rotational in a minute. That also is a form of energy. So something that rolls down a hill, if something rolls down a hill, you might have to account for both its, right here that's potential energy. When it gets here, the potential energy is gone, but it might have kinetic due to translation and due to rotation. Okay? So, and the fact that it's rotating, if some of the energy is in rotational motion, that means it has less in translation. So it'll be moving slower than a block which slid down there without friction. It's not rotating. Okay? So, so that was energy. The next thing we looked at was momentum. So, I forgot one on energy. The way to find the energy transferred, one way to find the energy transferred is take the difference in the final initial energy. Another way to find the energy transferred is to take the force times the distance it's applied, but you have to worry about the directions. So if you apply a force on a shopping cart and you push with a force of 10 newtons for a distance of 2 meters, you transfer 10 times 2, 20 joules of energy to the cart. Okay? If they're not, if these guys are perpendicular, the cosine of 90 is 0, right? So if you apply a force but it doesn't move it, you haven't transferred energy. Right? I can push on the wall all I want, and I might get tired, but I haven't transferred any energy to the wall. The wall doesn't have any more energy before I started pushing than when I had after, right? It's got to move in the direction I push it to transfer energy to it. Okay? And then with this one came the second area graph, graph the force and the distance the force is applied, assuming they are in the same direction, then the area under the curve is the work. So force times distance, if they're constant, if they're not constant, it's the area under the curve. Okay? Because technically the definition is FDX. All right, momentum is what we use when two or more systems interact, because even when energy is not conserved, momentum always is. So momentum is a restatement of Newton's law. If you did F equals ma and you rewrite it, you can write it as F times delta T equals delta P. So is that any reference?
Yes.
I think so. Let me slide the video camera over here. Whoa. There we go. So the idea here is that another way to think about Newton's law is to think about a system, and an external force will change the momentum of the system. Okay? So this is basically saying the force equals the mass times the acceleration, which is delta V over delta T. Bring the delta T up here, and m times delta V is delta P. Okay?
Yes.
So this is the impulse momentum theory. So do they write delta P or F equals delta P over delta T, I think?
They do delta P over that.
Yeah, okay. So they write like that.
Yeah.
So the thing to remember here is that this momentum is a vector. So going 30 miles an hour and then stopping, that's a change in momentum. Going 30 miles an hour and bouncing back at 20 miles an hour is a bigger change in momentum. It takes a larger force to stop it and reverse it than just to stop it. Okay? So you could have a momentum of an individual system or an individual object or a system, and usually we use momentum when we have two or more things interacting. Because if one car collides with another, the momentum of the first car might decrease, but the momentum of the second car must increase, and the total must be the same. Okay? So for a system, the change in momentum must equal 0 if there's no external forces. Okay? So if there's no outside forces, two objects are colliding or interacting, the total momentum stays the same. So if one of them loses momentum, the other one gains momentum. Okay? So on a graph, the total momentum, P, has got to stay constant for a system. For one object, it might be this, and then it drops down to that. But that means that for the other object, it's got to be about this, because they got to add up to the dotted line, right? And then it's got to jump up like this, so that the sum is still constant. Okay? So if there's no external forces, you have an isolated system, two or more objects interact, and you use momentum. So if a car is zooming along and it smacks into another car and they stick together and move off together, it's momentum. Momentum initial, but people momentum final.
I was going to ask about if you could go over the elastic and inelastic.
Yeah, so a special case of collisions is when energy is also conserved, and that was called elastic collisions. That's a very rare, and in practice never happens, but we can approximate it with, for example, magnets and stuff. If you know it's an elastic collision, you can use momentum or energy.
Okay.
But if it's not, you can only use momentum. So the classic question is, which of the following is true? Momentum is conserved during elastic and inelastic collisions, comma, energy is conserved in inelastic only. Or something, like they give you some choices, right? The thing to remember is, if there's no external forces, momentum is always conserved. It doesn't matter whether it's elastic or inelastic. It doesn't matter what kind of collision, whether they hit and stick, whether they bounce off of each other, whether there's Velcro or silly putty. It doesn't matter, momentum is conserved. Okay? But energy is not always conserved. Mostly, very rarely is it conserved. Okay? So they'll try to trick you. They'll say, what kind of collision is momentum conserved? Elastic and inelastic? Elastic only, inelastic only? Momentum is conserved all the time. Energy is only conserved in elastic collision. Okay? So, in this case here, if you have a system, an isolated system, P final equals P initial, so that's where you get the, M1 V1 plus M2 V2 initial equals M1 V1 final plus M2 V2 final. You can make up an equation and add up. You'll be missing something. If they hit and stick together, then obviously these two are the same. You can write M1 plus M2 times V final. But that's a collision problem. Okay, and we use, so when you have one object and you're looking at its motion as it moves because of gravity or something, generally you use energy for one object. If there's more than one object interacting, then momentum is the way to go. Okay. The other important thing about momentum, if you have a system of objects, the center of mass is only affected by external forces. So if the center of mass is at rest before a collision or explosion, it'll be at rest after. And if the center of mass is moving at 2 meters per second before the train cars collide, it'll be moving at 2 meters per second after the collision. Okay. So if the center, if I'm standing on a long raft, the center of mass is over there. The center of mass cannot move if I'm on the raft because there's no external forces. So if I walk to this end of the raft, where's the center of mass? Same place. The raft had to move that way, right? So center of mass cannot move unless there's an external force if it's at rest. Okay. So that was momentum. So that was kind of the big 4 units. Then we looked at a couple of special cases. So the next thing we looked at was gravity and circular motion. And so here we kind of generalized the force of gravity, M times G, was a special case. What's really true is that any two objects, the force of gravity is given by G M1 M2 over R squared, where R is the distance between their centers. That's an inverse square law. G is the universal gravitational constant. It's on the sheet, I think on the other side. Yep, and the units are on there. They'll tell you what units you got to use.
I'm assuming units are pretty important on this test.
Very rarely do they make a unit conversion. You'll almost never get tripped up because they give you something in miles. They don't do that. They don't give you something in millimeters. Yeah, so you don't need to worry about, you should write units when you solve problems. There might be a point for consistent use of units throughout the problem. Like a 10-point problem might have 1 point for consistent use of units. But they're not going to trick you. Okay, so yeah, a lot of my problems I would throw in millimeters or something just to, keep you, and they'll do that in college, but on the AP exam, no unit, they won't give you a problem in miles. Unless they give you the speed in miles per hour and ask for the answer in hours. So you don't remember that. So the force of gravity is more general than just M times G. The thing to remember is that if you happen to be on the surface of the Earth, you can go ahead and pre-compute this, and you get little g. So if you ever need to find little g, just take g times the mass of the planet divided by the radius squared. These usually come in relationships. If a planet has twice the radius of Earth, but the same mass of Earth, what would g be on it?
I don't know how to go with Earth.
So g is 10 on Earth, right?
Yes.
If you had another planet that had the same mass of Earth, but it was twice the radius. If the radius got 2 times bigger, what would happen to g? It'd be 4 times smaller, or about 2.5 meters per second squared. Okay? And we're going to use 10 for g on the exam the whole way.
The whole
10. Yep, use it for your problems, use it for the concepts, the whole thing. Okay? The other thing you just got to remember is that the density, of course, is the mass divided by the volume. So if I had a planet that was twice the radius of Earth, but the same density as Earth, then if its radius was twice as big, its volume would be 8 times as big. So its mass would be 8 times as big. So if you make the mass 8 times bigger and the radius 2 times bigger, that's 2 squared is 4, right? G would actually be 20. If it had the same density as Earth, but twice the radius. Does that make sense?
Yeah.
That's different than saying it's the same mass of Earth, because mass scales like R cubed for spheres. Okay. The other thing that we threw in here is we said that there's actually a way to calculate the potential energy when you're moving distances that are great, you're not on the surface of the Earth. When you're on the surface of the Earth, you can calculate the change in the potential energy with mg delta y. But it turns out that the actual potential energy you have because you're stuck on the Earth is minus g mass of object 1, mass of object 2 divided by r. So that was the one where we asked how much work does it take to get something off the planet? Far away, right? So to find the work, so since you guys are in calculus, to find the work, of course, it's the integral of the force, which is g m1 m2 over r squared times the distance you move it, which is dr. And if you integrate that from the radius of the planet to infinity, you get, this is all constants, the integral of r to the negative 2 is negative r to the negative 1. Right? So that's where that comes from. You don't have to know that. You just need to know that when you're on a planet, when you're in a gravitational field, your actual potential energy, not relative, but actual the amount of energy you need to escape, would be given by this. And if you want to know what is the escape velocity, how much kinetic energy must it have so that it can escape, you set this equal to the kinetic energy and solve for v, the velocity. That's the escape velocity, right? I ordered a t-shirt. Wednesday's like, wear your t-shirt for your subject day. So I found this t-shirt. I hope it's here on time. It's supposed to be, I found a way out of here. You know, it's got the formula for the escape velocity.
I don't know if a lot of people know.
I don't care. I'm going to wear it next year when I do that lecture. You know that. The other thing about this is, if something's moving in a circle, it requires a force to make it move in a circle. And so on your sheet, for circular motion, we had that the acceleration to make something move in a circle is v squared over r, which it's more useful to think about as multiply both sides by m, and you get the centripetal force is equal to mv squared over r. When something's moving in a circle, a force has to be applied to make it turn, right? And how much force you need is mv squared over r to make it move in a circle. Does that look familiar?
Yeah.
So on your equation sheet, it's this version. Now here's the important thing. Does this force do any work? You got a string, you're spinning a rock in a circle. Does the string exert a force on the rock? Yeah, the tension. Does it exert a force on the rock? Yeah, it's got it. Make it move in a circle.
Yeah,
but does it do any work? Does it transfer any energy to this rock?
I don't know.
After spinning it for an hour, does the rock have any more energy than it had before? No, because it's moving this way, and the force is perpendicular to the direction it's moving. It implies that the angle at all times is 90 degrees. Right? A centripetal force on something moving in a circle doesn't do work. Okay, that's a kind of conceptual question. Now be careful. If it's not perpendicular, it might do some work, like if you're moving in the ellipse. But I'll show you that in a second. Well, I don't know. If you put these two ideas together, you get orbital motion. Okay? So for orbital motion, you have an object in the middle, m, and you have some object, little m, orbiting it. And you can describe its motion by saying that the force that makes it move in a circle is the force due to gravity. The force making it move in a circle is little m, v squared over r, and that must be equal to g big M, little m, over r squared.
Yes.
And then you can solve for the velocity. How fast must it be moving to move in a circle? And you can say the orbital period, the time it takes to go around, is equal to the distance it goes, which is 2 pi r, divided by the velocity. Right? Does that make sense? Is that right? Yeah, the other way to think about it is its velocity is the distance it goes, 2 pi r divided by the orbital period.
That's how, yeah. But it's the same thing.
Same thing. Yeah. And then you can substitute that into there and you can solve for the orbital period. The important thing is, one of the important things is that the mass cancels. So if the mass of the satellite doubled, what would happen to its orbital period? Nothing. Yep. Does that make sense? All right. So that was gravity and circular motion. Let me slide my camera over a little more here. Clear out the room so I can just keep rolling it. It's like it's on a cart, pan zoom cart. There we go. So the next thing we looked at, I think was rotational motion. Rotational physics. And so the idea is that everything we've studied so far can be applied in a rotational world. And so when an object is rotating, we can describe its rotation. So if you have a rigid object, like a stick, and it's rotating, you can describe how far it rotates by theta. You can describe, so this is rotating. You can describe its angular velocity with omega, and you can describe the rate at which it is changing its rotational velocity as alpha, the acceleration. And there are kinematic relationships between those three, and they're exactly the same as those. Right? Just make sure you're in radians mode here. Sometimes you might be in degrees mode because they gave you 30 degrees, so you put in degrees mode to find this, right? You're gonna get 30 or 60 degrees, and those are easy, so I would just stay in radians mode. But, so I'm not gonna write out the kinematic equations again, but they're on your sheet, I think.
Yeah, they are.
So you can describe rotational motion using these equations, these variables, right? The only difference is here we have the period, which is the time it takes to make one complete rotation. Okay? So the period, time for a complete rotation, is equal to the distance you, let's see, the distance you go, so one complete rotation is 2 pi r, and that equals, no, the distance you rotate is 2 pi, and that equals the period times the velocity. So that gives us one of the formulas we use a lot, which is that the period equals 2 pi over omega. And that's down there, we use that in harmonic motion. The period of an oscillator. That's where it comes from. We have rotational inertia, so we can write Newton's laws, we can talk about dynamics. And so in dynamics, angular accelerations are caused by unbalanced torques divided by rotational inertia. So that requires a little bit of work. Remember, a torque is a force times the distance it acts. So if you've got a rigid object and a force acts on it that tends to rotate it, the rotational force, the torque, is F times R, and it's times the sine of the angle between F and R. So if you have an object pivoted right here, applying a force out on the end, but in this direction, doesn't do you any good. It doesn't cause a rotation, no matter how hard you push. That's because the angle between the torque and the radius is 0, right? Sine of 0 is 0. So you get the most torque when you're perpendicular. That's the idea, all right? So sometimes we write it's the force times the perpendicular NR. So you can think about that if you have a rigid object. Here's my rigid object. Here's my pivot P. If I apply a force like this, I can think about the perpendicular moment arm. That's R perpendicular. So the torque will be this force times its shortest distance between the force and the pivot. So think about it. If you're pushing on it like this, what's the shortest distance between the line of the force and the pivot? 0. There's no torque. Okay. So that was torque. So it's the angular, and of course, you always think about net torque. If there's a torque going this way and a torque going that way, the net torque is what causes the angular acceleration. I is the rotational inertia, which for rigid objects is just calculated using calculus, and it's given to you, and it'll be given to you on the problem. So it'll tell you that for a sphere, the rotational inertia is 2/5 mr squared, for example. Okay. So that's the rotational inertia. The thing to remember is that we got it, the rotational inertia we got, by taking each mass times the distance from the pivot squared. That's how we got rotational inertia. And so if an object gets twice as big, its rotational inertia gets 4 times bigger. It's proportional to its radius squared. Okay. And we actually summed these all up. Remember that lab, the spreadsheet? We broke a meter stick into chunks, and for each chunk we found M and R squared and added them all up. That's the idea there. You don't have to.
No, I don't remember.
Remember it?
Yeah.
I don't know.
Really? Okay.
Look,
to be honest,
I'm probably gonna do the labs to the best of my ability.
Okay,
I mean, I tried. I remember
that's
something.
okay. So that's alpha, the angular acceleration. So this is Newton's law, okay? You can talk about angular momentum, and so instead of the impulse momentum theorem, you can say that the torque, the net torque, times the time that it is applied causes the change in the angular momentum. So we can define angular momentum as I times omega. Instead of mass times velocity, we use the angular components, right? So the angular momentum is I times omega, and if you want to change the angular momentum of a system, you need an external torque. If there's no external torques, the angular momentum of the system cannot change, so the angular momentum initially is equal to the angular momentum finally. And so that's the problem. So like the skater holds the weights and you spin, you pull your arms in, right?
Yeah.
If the angular momentum changes, if the angular inertia changes, I bring my arms in, the moment of inertia, the rotational inertia gets smaller. Yeah, because it depends on the radius. If I make it smaller, I get smaller, then if I get smaller and L can't change,
Then
omega gets bigger.
velocity
Has to increase,
Yeah.
right? So that was conservation. So you're looking at systems where there's no external torques.
Yeah.
Just like here, when there's no external forces, momentum is conserved. When there's no external torques, angular momentum is conserved. And then the other thing we threw in here was angular energy. The kinetic energy of something rotating is equal to 1/2 I omega squared. And when you have balls rolling down a hill without slipping, the thing to remember is that if you're not slipping, your velocity is equal to omega times r. So that allows you to solve problems like how fast is the ball going at the bottom of the hill, okay? Or more common, or maybe not more common. Suppose I have a ball rolling, it's moving and rolling without slipping, and it comes to a hill. How high up the hill does it go? Well, you can say that its kinetic energy at the beginning, which is 1/2 mv squared plus 1/2 I omega squared, must equal its potential, which is mgh. And since omega equals v over r, you can write this as 1/2 mv squared plus 1/2. I is usually like 2/5 mr squared, and omega is v squared over r. And so the r's cancel.
Yeah, I remember that.
So, and that gives you mgh, and then all your masses cancel,
Yeah,
and you
it's
can
nice.
solve for h.
Yeah.
So the rolling without slipping is the key word that allows you to relate the velocity of the center of mass with the rotational velocity.
Okay, let's say it's rolling with, or like it's rolling and it's slipping.
You can't solve that
Okay.
problem.
I can't solve it, so that's
Yeah,
good.
you
That's
can't
good
solve that
news. That's
problem.
good news. I like that.
Yeah. I mean, if it's rolling and it's slipping, then there's no relationship. So that would be a conceptual question.
Okay.
So if it starts slipping as it goes down the hill, then it doesn't spin as much, and less energy is rotational, so more energy must be translation. So a ball that rolls down and slips will be moving faster than a ball that rolls without slipping.
Yeah.
So that's about the only way you'd see that.
Okay.
Okay.
That's pretty interesting.
So that was rotational physics. And one more. The last thing we did was harmonic oscillators. And there's a bunch of equations in here, right? So first of all, oscillators. First of all, we have to know that a spring exerts a restoring force, so the force that a spring exerts is minus k times delta x. How much force a spring exerts depends on the distance it stretched from equilibrium. You stretch it more, you stretch it twice as far, it's twice as much force pulling it back. It's restoring, meaning the force the spring exerts always opposes displacements from equilibrium. Okay?
Yeah.
When you have a linear restoring force and you disturb a system, you get simple harmonic motion. And the period, the time it takes to complete the cycle for a mass on a spring is equal to 2 pi square root of m over k, where k is that spring constant, the strength of the spring. You can show that for a pendulum, the restoring force is proportional to the mass and the length of the string. And so for a pendulum, you get 2 pi square root of L over G. The mass cancels. The restoring force has the mass in it. It's mg over L, I think is what we worked out. You don't have to know that. When you plug that in there for K, you get L over G. The mass is canceled. So if you double the mass of a pendulum, what happens to the period? Nothing. If you double the mass of a mass on a spring, what happens to the period?
1.4 times.
It's bigger by the square root of 2, right? 1.41. Yep.
Some.
If you have a simple harmonic oscillator, its motion is periodic and it can be described by a cosine function. So a simple harmonic oscillator can be described by the function, well, its motion is a sine wave. So if you have a simple harmonic oscillator, its motion looks either a sine or cosine depending on whether it started at its equilibrium position or at its maximum displacement. If it starts at its maximum displacement, it goes like this. It's a cosine wave. Okay? And in this case, the period, you know, the mass on a spring, so you know the period of it. So we're talking about, you pull a mass down, you let it go, and it vibrates, right? It goes up and down. The period, you know, the mass on a spring. We can describe its motion using the equation, the y position as a function of time equals the amplitude times the cosine of, and I never remember what they have it here, plus y naught. I'm going to put omega.
They do have omega.
They put omega?
Yeah.
Okay. And so remember, omega, that's the angular velocity. But this thing's bouncing up and down. Right.
Sure.
You can map it to the motion of a wheel turning, right?
Mm-hmm.
And so you could also, omega also equals 2 pi times the frequency, which is 2 pi divided by the period. So that's an equation there. So if you know the period, you can find omega to describe its motion. Right? If you know the period, you can find omega. You see this equation down there?
Yeah.
No, that's the one, but down here, it gives you the relationship, there. The period is 2 pi over omega, which is 1 over the frequency.
So yeah.
I mean, I guess the worst case where you just look at the equation. Like, they have to give you something.
Yeah.
I was thinking about this. I think, like, writing down the variables that it gives you, I feel like, or at least, like, just identifying what they give you.
Making
is
a
so
variable
important.
list.
I think it's so, because you
Yeah.
can only do so much with it, and if you
Yep.
just, like, look at what they give you.
Yep. You just gotta know what they're giving you.
Exactly.
If they say it rotates with it takes 15 seconds to make a complete oscillation, you gotta know that's the period, right? So the other thing here is if you think about a simple harmonic oscillator, so imagine you've got a spring connected to a block, and the block is vibrating back and forth, okay? Its equilibrium position is x naught, and it goes all the way over here to x max, okay? When it's pulled all the way to x max, you have stored energy in the spring. How much energy you've stored can be found because you know the force is k times delta x, and if you stretch it a distance a, this will be k times a, and the area here will be 1/2 k times a squared. And that, of course, is the work you did, so that's the energy it has. So for a spring, the energy it has, the potential energy, is 1/2 k times the distance it stretched squared. So that's on your sheet, right?
Can you just, like, go through that whole triangle business, but it's a little bit slower?
Okay, if I have a spring, and this is the force I exert, and this is the distance the string is stretched, right? Let me call, yeah, okay. So, because it's a spring, I know that the y equals, this must be the slope, k. I'm worried about the absolute value. So the slope is k, right?
Okay.
So if I stretch it to some distance a, how much energy did I store? Well, it's the area under here, right? Because force versus distance, the area under the curve is the work you've done.
Okay.
So the area under the curve is the base which is A, times the height, it's 1/2 the base, times the height. And if this is A and the slope is K, the height is K times A. So K times A. Okay. And that's where we get 1/2 K times the distance of stretch squared. Okay? So this is the formula on your sheet. The energy in a spring, U sub E. See it there? U sub E, the energy stored in a spring, is 1/2 kx squared. The thing to remember though is that x is the distance it's stretched from equilibrium. If equilibrium is at 40 centimeters and it's pulled to 50 centimeters, you don't use 50, right? They wouldn't say centimeters. If equilibrium was at 0.5 meters and it's pulled to 0.6 meters, the distance is stretched is 0.1. Okay? Now, that is potential energy. When I let it go, it oscillates, right? The energy, as long as it's frictionless, sloshes back and forth from kinetic to potential. So, whatever kinetic energy it has, and this is the most important equation that's not on your sheet, whatever kinetic energy it has, 1/2 mv squared, plus whatever potential energy it has at some arbitrary point, which is 1/2 k times the distance from equilibrium squared. That's got to add up to the total energy, which is that. So if we give you if you know the mass and you know the spring constant, and we give you how far it's stretched from equilibrium, you can find its velocity. When it's at equilibrium, this is 0, and so you can find its maximum velocity. Okay? And if you set that equal to it, you get 1/2 mv squared equals 1/2 k a squared. The 1/2s cancel, and you get that the velocity max equals, let's see, k over m square root times a. Is that right? Yep.
Yeah.
Which is omega times a. Because omega is k square root of k over m. Right? The period is 2 pi square root of m over k, or 2 pi times omega. Right? Because we know the period is 2 pi. Omega over 2 pi is upside down.
I think it's upside down.
Yeah, it's upside down. Sorry. K over m. That's 1 over omega. Okay. But you can work all that out from that one energy equation. So that's important to be able to construct for a harmonic oscillator. This energy equation. Total energy is conserved for a harmonic oscillator. And anything that links more than one section of this board together is a problem you're likely to see.
Yeah.
They like linking gravity with circular motion. Energy with something rotating, right? Ball rolling up down a hill. Harmonic oscillator with energy.
Yeah.
Something moving along and it smacks into an object, there's a collision, and then they compress a spring. So you have a problem where you got to find the velocity after the collision, and that becomes the velocity of the harmonic oscillator. How much does it compress the spring? So you need the kinetic energy after the collision, so find the velocity after the collision. Find the kinetic energy, that becomes the energy that compresses the spring. Okay? So I think that gets us through everything that's on the exam. All these equations were cut out of the AP exam. All of the waves and all of the electricity. So basically mechanics is all you got. And I think we just touched on all those equations. Are there any that I'm missing? I think I got all of them. So, honestly, it's all application, right? There's not a whole lot of content knowledge.
Yeah.
I mean, it's all there, and you have the reference sheet.
Have the equation.
You have the equation sheet. So, it's just about working out the relationships. And there's lots of questions about relationships. You know, if this gets 2 times bigger, what happens to that?
Mm-hmm.
So you gotta know, if the length of the pendulum gets 2 times bigger, what happens to the period? It's the square root of 2 times bigger. If you take a mass on a spring to another planet where g is twice as big, what happens to the period? Nothing. take a mass on a spring to a different planet. What happens to the period? Nothing. G's not in here. Doesn't depend on G, right? So, questions about relationships pop up often in the conceptual questions. You'll have some kind of question on the free response section. There'll be about an object sliding or rolling down a hill. Find the velocity at the bottom. It then gets launched horizontally. So all that projectile motion problems are all back here. Remember, if something's launched, you can treat its motion horizontally, separate from its motion vertically.
Different components.
Right, and horizontally there's no acceleration. So its horizontal velocity is constant, its vertical velocity it changes. So let's just do a little practice problem here. If I launch a ball and it goes through the air, at point A, what is the acceleration vertically? Yeah, the trick, everybody thinks it's 0, right?
Yeah.
What is true at point A? You need to know that the velocity in the y direction is 0, but the acceleration in the y direction is still negative g. Okay? And then at any other point, at point B, what's true? The velocity in the y direction is positive, but the acceleration is negative. Okay? There'll probably be a question on there. It seems like this is usually where you have some sort of graph showing, the position of an object. Goes like this. How many times does this object change directions?
Change direction.
So you just got to think, what does it mean to change directions? It means your velocity changed sign. So your velocity is the slope. When did the slope, how many times did the slope change signs? 1, 2, 3, 4. Right?
Yeah.
If this was the velocity, how many times does it change directions? Just once, right there. That's where the velocity, just keep those in mind.
Yeah.
Something is speeding up if its velocity is increasing, its position is. So if this was the position, right? The lifting goes like this. So let's call this A, B, C, and D. On what time intervals is the object speeding up?
So whenever the slope and the acceleration is the
So is it speeding up from 0 to A?
Yes.
That's a better question.
Well, because
Think that. Think this.
They have to be the same sign.
they have to be the same size.
Yeah. They could be the same sign.
Yeah. So
Yep.
just calculus.
Yep.
Calculus. Simple as that.
It's all calculus. Speeding up when it's the same sign.
Yeah.
So that's in a nutshell. I mean, yeah, but you guys will be fine. Just work through it, take your time.
Yeah. I think just identifying what the problem gives you, and just going from there.
Yeah, and it's a bummer that it's been 6 weeks.
And they flew by. Honestly,
Yeah, fourth quarter went fast.
I can't believe it.
So, yeah, so that's in a nutshell, guys. Does that feel like it jogged your brain a little bit?